class here. So something nice happened, kind of by accident, but it's going to be permanent now. Last semester they ran out of time. They were supposed to cover Newtonian gravity, didn't have time. They said, oh, do it in this course. But then we talked and we're like, you know what, actually makes more sense in this course because Newtonian gravity is basically identical to electrostatics, right? It's another field theory, basically identical. We're going to cover it here today and Friday. So let's get started. Right, gravitation, supposed to be last term, didn't happen, so we permanently moved it here because it's actually a better fit. The mathematics used for electrostatics, particularly the electrostatics of point charges, is identical to what we're going to be doing here today. So that doesn't mean you haven't used gravity, right? You've used F equals mg, certainly more than once since you got here to university. F equals mg, it's still true. It's still a thing. It's just the magnitude of the force of gravity near the Earth's surface when we use that classic 9.8 meters per second squared. What we're going to talk about here today is that gravity will exist everywhere. It's one of our four fundamental interactions in nature, and it's something that is a vector relationship very similar to the electrostatic phenomenon. So here's the four fundamental interactions in nature: gravity, electromagnetism, the weak and strong interactions. So these are sometimes referred to as the weak and strong nuclear forces. So those of you who want to get into stuff like engine physics and do nuclear engineering and stuff like that, you would learn a lot more about these two at some point. For now, we're just, in this course, we mainly focus on electromagnetism, but now we're going to cover another one of the fundamental interactions, which is gravity. Okay, so these fundamental interactions, aka fundamental forces, these are the things everywhere we look in nature, we can basically explain everything in terms of these four things. Okay, and we have different physical theories that describe each of these things. Oh, and they get to start things off. So I want to show some cool gifts here just to show why there's some things we can learn with gravity. So last semester you would have learned about uniform circular motion. Turns out the circular orbit problem at a constant speed is just a uniform circular motion problem, where the speed is a constant, the force is always pointing inwards. So instead of having a ball on a string like last semester, the force of gravity is always pointing inwards and being that central force. So you can understand orbits using this. And this is basically what Newton did, and why the thing that was so profound that Newton did. Yes, Newton introduced Newton's laws of motion and the gravitation law, but what was so profound that Newton did is to use the laws of motion combined with the law of gravity from here on Earth to explain the motion of the planets. Okay, so we'll talk a bit about that in the next couple of days, not too much about it, but basically planetary motion can be described using this physics. And of course it's much more complicated in general. You have planets going around the sun, you have moons going around the planets. Orbital phenomena can all be described using this Newtonian gravity we're going to talk about here. So Newtonian gravity, it's a general law of gravity everywhere in the universe. It was proposed in 1687 in the famous Principia by Newton. So essentially what Newton did in the first part of the Principia was introduce the laws of motion. In the second part, introduced the gravitation law, and then the third part combined them to make an equation of motion whose solution was elliptical orbits for the planets around the sun. So it's commonly referred to as the crowning moment of the scientific revolution, where everything really came together, where the ideas of motion and gravity on Earth could explain something in outer space. It was a very profound achievement because it wasn't obvious that what's going on up in the nighttime sky could be explained by laws of physics here on Earth. So what do? we introduce what we call the gravitational field. Now G is going to be a vector field, kind of like the electric or magnetic field. It's going to exist everywhere. We're going to have a bunch of vectors, for example, due to the Earth, pointing in towards the Earth. It's very similar to the electrostatic field. Okay, so the Newtonian gravitational field is going to be G. We have a bunch of vectors pointing inwards. How do you create a gravitational field? You have mass present. So kind of like a charge sitting there would make an electric field around it, a mass sitting here will create an electric or gravitational field around it. So what does this gravitational field look like? Well, essentially you have some mass. Could be a planet, or it could be you or me, or everyone who has mass has a gravitational field around them. The reason we don't all collide into each other in this room is the Earth is so much stronger that the net force, as we'll see today, or Friday, I guess, would be very much predominantly due to the Earth and not each other. But we do create a non-zero gravitational force on one another. Anyway, so we define this thing, the gravitational field, is a bunch of vectors pointing in towards the object. And as we get further away, the magnitude of these vectors gets smaller and smaller. So we have a decreasing gravitational field further away from the mass, and the vectors are bigger the closer we get. So, Newtonian gravity, unlike electrostatics, there's no repulsion in this theory. If you have two masses, water bottle, stick, there's only attraction. Positive masses attract one another. This is one of the differences with electrostatics. In electrostatics, you need a negative charge and a positive charge for attraction to occur. In gravitation, positive mass, they will attract one another. Now there's three postulates of Newtonian gravity. There's the force law, the principle of equivalence, and the statement that the laws of motion are universally applicable. The third one we kind of take for granted now, but Newton separately postulated this to say, hey, all this stuff I'm describing on Earth, we're going to assume everywhere out in the space that this stuff works too. So let's go through these. First is the force law, proposed by Newton. Now I believe if you actually look at the Principia, it is more of a proportionality, like force is proportional to the masses times each other divided by r squared or something like that. It's our more modern form of it, which is that the force, the magnitude of the force of one object on another object, and vice versa, is the same. It's g times the one mass times the other mass divided by the distance between them squared. Now, so vector-wise, these vectors are equal magnitude but opposite direction. So this one has a vector going this way due to this one's gravitational field. This one will have a force vector going this way due to this one's gravitational field. And that's how the attraction happens, is the force vectors point towards one another because they're equal and opposite. And this G here, this is kind of like the constant K we had for electrostatics. It's known as the gravitational constant, 6.67 times 10 to the negative 11 meters cubed per kilogram times second squared. This law here is Newton's gravitational force law, kind of like Coulomb's law in electrostatics, which was K Q1 Q2 over R squared. But this is a general vector law, just like Coulomb's law. So in high school, you probably would have seen what was on the previous slide. This is the more general vector form, which is almost identical to Coulomb's law. The force of one mass on another is equal to gmm over r squared r hat, where these r's are the same thing we did before. Nothing has changed. These big r's are going to represent the same notation as we did for the electrostatics unit. The only change here is we have to add a negative sign in the Newtonian gravitational force law. The reason is, for electrostatics, opposite charges attract. For gravitation, Same mass, like positive attract. So we need a negative sign here to account for that difference. In electrostatics, if we have Q1, Q2, one is negative, one's positive, that's where the negative sign comes from. Okay, so here we have to kind of put it into the law itself. We need that negative sign in the Newtonian gravitational force law. So what does this vector look like? Let's say we have two masses here, big M and little m. The force on little m due to big M is a vector pointing back towards the object causing the force. So if this is like the moon and Earth or something like that, we would represent a force vector acting on the moon, which is a central force, which is always pointing back towards the Earth, kind of like a string when you spin a ball on a string. The tension in the string is the central force for the ball on the string problem. For orbits, the force of gravity takes the place of that central force. So we have this Newtonian gravitational force law, and that'll dictate the force on masses due to each other. All right, let's get to the next one of Newton's gravitation postulates here. This is the principle of equivalence. This one kind of seems obvious. We kind of take this one for granted. But Newton introduced the MA law, right? Newton's second law. In the MG law, the gravitational force law, it's not a given that the mass quantity here is the same as the mass quantity here. In other words, it's not a given that this, what we call mass gravitationally, is the same as what we call mass inertially. So Newton separately postulated this, that the inertial mass and gravitational mass are the same thing. So you can cancel the m's, and you get the result that the acceleration due to a gravitational field is independent of the mass. Okay, this was important for a couple reasons. One, Galileo, we'll talk about that in a couple slides here, but Galileo had done a bunch of experiments showing that objects fall due to the gravitational field independent of their mass. And later, many experiments have tried to distinguish these masses. They all come back that they're the same. So, this is a statement of Newtonian gravity. And the final postulate is that these laws are universally applicable. The reason this was important at the time is, as I said, it was absolutely not obvious that the nighttime sky was somehow related to the laws of physics on Earth. It's a very fascinating story where some individuals collected data of the planetary motion over a long period of time, interpreted it, and figured out that the planets were going around the sun in elliptical orbits. So what Newton did is to combine MA with the gravitational force law, solve that equation of motion, you get the path of an ellipse exactly like they saw in the data. So it's a very remarkable achievement, the crowning achievement of the scientific revolution that was accomplished using the type of stuff we're talking about today. Okay, so most of this lecture is focused on introducing what we call the gravitational field. You can think of G vector, the gravitational field, as being very similar to what the electric field vector was around a stationary point charge. So the electrostatic theory is virtually identical to the Newtonian gravitation theory. So what do? Well, we introduce something called the gravitational field of an object, let's say it has a mass big M, where G vector is negative Gm over r squared r hat. That is almost identical to what we had for the electric field due to a point charge. Again, the big difference is this negative sign, which accounts for the fact that positive masses attract one another, opposite charges attract one another. So we need a negative sign to essentially flip the direction of the field vectors given the charge or mass. Why? Well, a negative charge has vectors going inwards. A positive mass has vectors going inwards. We flip it with that negative sign. Now, if we take all that stuff and write it as G, what do we get? The force of a mass on a mass in general is mg. The mass of the object replaced in the gravitational field times the gravitational field that it is in. So let's think for a second. What does this remind you of in electrostatics? What was the force in electrostatics? QE. Charge times field. Mass times field. The way in which we calculate force in electrostatics compared to Newtonian gravity is the same basic relationship. We multiply the parameter associated to that field theory, which is mass, times the field itself. So F equals QE, F equals mg, very similar for the two theories. So let's compare them. I still remember back when I was your age learning this stuff. This is one of the things that I thought was so cool. One of the things that I was very interested in physics to begin with, but this is probably one of the main results that got me really fascinated in physics, which is that when you compare the gravitational field and force, you have virtually the same relationships as in the case of electrostatics. So for Newtonian gravity, you have F equals mg. For electrostatics, you have F equals QE. Formatically, the same expressions for force. What about the fields? You have a constant times the mass over the distance squared, a constant times the charge over the distance squared, times the unit vector of that big R vector. The only difference being the negative sign here to account for the difference in attraction loss in the two theories. Okay, so it's super cool stuff. We have here that electrostatics, very, very similar to Newtonian gravity. Pretty much everything we did in electrostatics, we can repeat, and we'll go over most of it, okay? Today we'll use some examples of finding the gravitational field, but it's gonna seem a lot like those ones we did because it's very similar. It's very similar. We're doing the same thing again for gravity. Again, the fields are just different by a negative sign. The electric field has no negative sign, the gravitational field does. And this is based on the statement that opposite charges attract, but like masses also attract. This negative sign accounts for this difference in the theories. Okay, so cool stuff. Let's talk a little bit about this gravitational field here. So a massive object has a gravitational field all around it. Every one of you have a gravitational field around you according to Newtonian gravity. How do you test the strength of a gravitational field? Well, you put a mass in it, right? You have an object, it has a field, you put a mass in it, you can measure the force, and you can determine the strength of that field. So just like charges in electric fields could be, had some force on them, masses in gravitational fields have a force on them, and that's how we can test the strength of these things. Okay, so these vectors g here, they get smaller the further we get away. F equals mg, we've been using it. How does this relate to last semester? How does this relate to your classic mg? Well, if you take the magnitude of this vector here, the magnitude of the g vector is just little g, which is g m over r squared. So let's say we plug in the mass of the Earth for m and the radius of the Earth for r, we work this out, we get roughly 9.8 meters per second squared when we do this calculation. So the 9.8 value is the magnitude of the gravitational field near the Earth. This is also something we can determine by experiment. Yeah?
Maybe like back in the time where we verify the radius of the Earth, like by how fast like the Earth will revolve around stuff, but how would they find that?
This is a brilliant question. I'm actually doing this on Friday. It's a good, great question. On Friday, it's a very cool story. We're going to talk about how they first determined the mass of the Earth. But it was from this relationship. Like you said, they could figure out the radius somehow. They could measure the g somehow. I believe the trick was figuring out the value of this constant. That was the tough part. Once they knew the constant, they could rearrange for the mass of the Earth and get a prediction. That's roughly speaking how, sorry, I should have said earmuffs first, just in case anyone didn't want spoilers for Friday. But anyway, basically 9.8 here, this is the value of G that we've been using all along. You can just plug it in here. Actually, there's a very cool lab I want to introduce in this course, or I guess the last course. One of the courses in first year, you can actually measure G by doing some experiments and making some plots where the slope is G, and you calculate the slope, and it ends up being roughly 9.8. So it's a cool lab to do to kind of measure this stuff. So the famous 9.8, that's near the Earth's surface. Galileo, as I said, had an important part in this story. Galileo figured out that objects in a vacuum fall with the same gravitational acceleration. You can look up on YouTube, there's some super cool videos of like vacuum chambers. They'll drop a bowling ball and a feather, and they're both going at the same speed. Super cool stuff. So Galileo had figured that out. So it's not like Newton did this all from scratch. Some people had some ideas before they kind of contributed to this theory. All right, so our gravitational field here. We want to calculate this thing. So we want to be very precise in the way we operate. How can we determine the gravitational field? At some point P. Oh, that's kind of like we've been doing for the other fields. How can we determine R and all this other stuff for G? Exactly like before. Okay, so we're going to do some gravitational field examples here. Super like before. The other thing is just a reminder, this negative sign, very important for the direction of the field. We want all the field vectors to point in towards the mass. If we didn't have the negative sign, all of the vectors would be pointing away, and we would have repulsion, and then we would all be floating, right? Actually, there was a cool art project someone submitted a few years ago when I was doing the art project. They did a graphic of like, the title was, "If you forget the negative sign in Newtonian gravity." And it was like a bunch of people floating away from Earth. It was a good art project. I'm looking forward to going through all the art projects. It's one of my favorite things. Just some hilarious stuff. Anyway. So, and it's due tomorrow, by the way, if you haven't got that announcement. But basically, we have this gravitational field expression. We want to calculate the G vector. So this G vector here, it's just like calculating E before. Sorry, I'm just going to adjust this right here. It's just like when we calculated E in the past. Basically, the only difference is the interpretation of what we're doing. So the interpretation changes a bit, but at the end of the day, this problem is almost the same. That's why we have this same figure here. I quite literally just went into Paint and replaced Q with M. That's how similar doing these problems is. This is the same figure we had earlier in the course. So we have a mass somewhere. We define the R prime vector as being from the origin to that mass. Then we have a point where we want to calculate the field. That's what we call the R vector. The big R vector is the subtraction of those two. Okay, so you subtract those two little r's, you get the big R. That's the one we need in our gravitational field equation. All right, so a quick reminder. As I said, this is just so similar to what we did in the past. You have this R minus R prime. You figure out what they are, you plug it in, you do the subtraction, find the unit vector, find the magnitude. It's the exact same process. So you shouldn't be, shouldn't be looking at this as a whole new thing to learn. Mathematically, it's pretty much the exact same thing. Let's do a couple examples here. We're going to place a mass right here at 2, 3, 0. We're going to place our point P where we want to find the field at 570, and we want to find the gravitational field at that point P. Now, one thing I'll note, you might be looking, oh, why did you pick 2 points that are kind of on a line like that? Well, I wasn't thinking much. I was doing it numerically and then drew the figure later, which is how this came out. But basically, if you do a rectangle that has sides of 3 and 4, then the hypotenuse magnitude is always 5. It just makes the numbers nicer for these examples. That's why this is like this. Anyway, so we have our mass here. We have our point P here. We know our r prime vector is 230 to go here. Our r vector is 570 to go here. We need to take the difference of those. So solving this problem, might as well have already done it, right? We just take our r minus r prime, plug them in, do the subtraction. You're left with 340 from subtracting your r minus r prime. You find the magnitude, it's 5. You divide by the magnitude, you get the unit vector, and then you plug all of that into G. So you have your definition of G, you plug in your unit vector and magnitude squared, you're left with negative gm over 5 cubed. 340 is the gravitational field vector at point P. So the process of calculating this, I'm hoping you're all very familiar with at this point, but if not, it's never too late to figure out these types of problems, right? Because now you have multiple reasons to know it, not just for the electrostatic problems, but also for the gravitational field problems. So that's our gravitational field. So let's say we had a specific mass, like 125 kilograms. We could plug that in for m. So 125 over 125 cancels. We could multiply the negative g in. We get negative 3g, negative 4g, 0 for the gravitational field. If that was an accident, I'm not trying to advertise phone plans or anything like that. It just kind of ended up like that when I did this problem. So we can take this vector and plot it. What does our g vector look like? Well, our gravitational field vector at point B is pointing straight in towards mass m. So our negative 3g or negative 4g, 0. It's some vector here pointing straight back towards the mass. And that's always going to be the case. That's the nice thing about Newtonian gravity. It's actually easier because there's only one thing that happens, attraction. You can't mess up which direction it has to be. The gravitational field must always be pointing inwards towards the mass. So you can double check your results just by drawing a quick picture like this. So anyway, the gravitational field points back in towards the mass, and we could do this everywhere on this grid. If all of the vectors would point back in towards this mass, the further out we get, the smaller the vectors would get, and so forth. What about the force? Well, the force is mg. So let's say we had a 2 kilogram mass. The force on that mass at point P would be that 2 kilograms times the gravitational field vector, negative 3g, negative 4g, 0, multiply this by 2, we get negative 6g, negative 8g, 0. So these are like foam plans of the future. And basically, this force vector here tells us what's the force on that mass due to the gravitational field. Okay, so if we know the gravitational field at a given point, the force of gravity there is basically the same as if we place a mass there times that gravitational field. Okay, right. So you can work with the gravitational field independent of any masses that are present, just like for the electric field. Okay, so as long as we know where is our mass, and where do we want to find the field, we can find G. Again, might as well be the same thing as the point charge due to electrostatics. So we can go ahead and find this for a variety of problems. SI units for G, meters per second squared. All right, let's do another practice problem here. We're just going to whip through this one because it's the same thing again. Remember, we did this for electrostatics. If you move the origin, you shouldn't change the physics. All that matters is the relative distance from the mass to the point. So if we move our origin here such that the mass is over here and point P is here, this is inevitably the same gravitational field, just different r vectors. So we take these new r vectors for our locations, like 2, 2, 0 here for point P, and we redo the problem. We get the exact same big R vector, 3, 4, 0, same magnitude 5, same R hat, same G. Everything is the exact same. This emphasizes the point, moving the origin does not change the physics, which it shouldn't, right? It should not change what actually happens physically when we move an origin from one location to another. All right. So we have this gravitational field vector. It's the same vector we found in the previous problem. If we place the mass at point P, we get the same G. If we place we get the same force. Everything's the same. We just move the origin, and that's what we expect for this type of stuff, right? So that's all good. Now, the note here on the r cubed in the denominator. Remember how when we did the electrostatic problem, we would get the cube in the bottom a lot? Sometimes we would say, hey, we don't want to work with unit vectors. Let's replace the unit vector. We can do the same thing here. You can replace the unit vector with r vector over r magnitude, and rewrite the gravitational field as negative gm over r cubed times the r vector. Okay, so you can do this as well for Newtonian gravity. You can just replace this unit vector, work in terms of r cubed. That's why we end up with the cube power of the denominator so much for this field type stuff. Nice. Someone predicted this in the morning. Someone said, wait a second, are we going to do a fun mass like we did a fun charge? Of course, right? Of course. When we talked about electrostatics, the fun charge, we said if k times q is equal to 1, we have what we call a fun charge, which just makes the math way easier. We can do the exact same thing for gravity. We'll define a fun mass as a mass such that gm equals 1. This should have an equal sign here, but the gravitational field for our previous problem was negative gm over 5 cubed 340. So if we had a fun mass, gm would be 1. We have negative 1 over 5 cubed we can multiply through. We have negative 3 over 125, negative 4 over 125 meters per second squared for our gravitational field. So yes, we could do fun masses again, just like we did for the electrostatics 2-point charges. All right, so we're going to talk a bit about plotting G here. So we have the gravitational field, negative g m over r squared times the r unit vector. Now, essentially, we could ask ourselves, how can we take this equation and rewrite it in a way we can plot on an x, y, z plot? Like, you want to see, what do all these vectors look like? Well, what we can do is we can place a mass at the origin such that r prime is 0. So big R is just little r. The gravitational field for a mass at the origin is in terms of little r, just like this. Now little r, remember, that's the vector to point P. So how do we get any point P? The vector x, y, z will give us any point in 3D space. So we can plug in any x, y, z here and figure any g vector anywhere in 3D space and see what it will look like. So let's plug in this little r vector here to our g definition. Well, little r magnitude, that's x squared plus y squared plus z squared square rooted. We know the unit vector, so we put it all together, we can get the gravitational field for any position in 3D space, and we can plug in any number we want in 3D space and get exactly what that vector will be. Now, this vector here, remember the cube, that comes from that cube power we just talked about. The over 2 comes from the square root. We often have this 3 over 2 exponent when we do these gravitational field type problems. So 3 over 2 is not uncommon to see here when you calculate this type of stuff. All right, so we have our gravitational field. We can take a bunch of numbers and plug it in and see what we get. So let's take this equation here and plug in a bunch of random numbers. We get something super cool. So here's a 3D grid here of what the gravitational field looks like. Everywhere close to the mass, we have larger vectors. So if you're very close to the mass, the gravitational field vector will be large. The further away you get, if you get further from the Earth, that vector will get smaller and smaller and smaller the further you get. So you can picture everywhere around a massive object, you have all these vectors pointing in. The bigger ones closer, the smaller ones further. In the case of electrostatics, if we said, hey, what's the field look like due to a negative point charge? It'd be the exact same picture, right? It'd be the exact same picture. So this is just like what we saw from the electrostatic field. All right. Next, the superposition principle. We know that from the electrostatics topic. We know that from magnetism. Turns out the gravitational field also follows the superposition principle. So if you have three masses, 1, 2, and 3, the total gravitational field at any point due to those three masses is the sum of the g vectors produced by each of those masses. So when you talk about multiple massive objects, what's the total gravitational field? You use the superposition principle the exact same way we did for electrostatics and magnetism and stuff like that. So you can just find all your g vectors independently and sum them all up. This greatly simplifies calculations, because let's say we have two masses on the y-axis here. Well, we know at some point P over here, there's going to be a gravitational field vector to the first mass, a gravitational field vector to the second mass. The total gravitational field vector here at point P is going to be the sum of those two vectors. We had G1 and G2, we get the total G vector. This total G vector is the one that dictates what the force will be. So the force on an object we place here at point P will be Fg. And if we had three masses, for example, well, the force would just be we add up all their fields to get the total field, and that's what dictates the force on the object, okay? So this is identical to what we did with electrostatics. Bunch of masses, the total gravitational field is the superposition principle of all of them. So we can write this compactly with a Riemann sum, just like we did in the past. So the total G vector is the Riemann sum of all of those independent G vectors. So basically, you add up all of them, you can write it compactly as a Riemann sum. This is virtually the same expression we had when we talked about electrostatics to calculate the total G. Final topic today is the scalar potential. Well, wait a second, in electrostatics, we introduced V, the scalar potential for the theory. Can we do the same thing in gravity? It turns out, yes, we can. So first, let's review electrostatics here. The negative change in potential is the integral of the dot product of E dot dl. So we add up E dot dl over some path, that's equal to the negative change in the scalar potential. On the converse, the electric field is equal to the negative gradient of that scalar potential. So here's how we define potentials for the electric field. Now let's look for gravity for some scalar potential phi. The negative change in the scalar potential is the integral of G dot dl. G is equal to the negative gradient of the scalar potential. So they're identical definitions. We can define a gravitational scalar potential in the exact same way we did for electrostatics. So these theories are virtually identical. The big difference is the negative signs in the fields. So for example, if we want to find the potential When we 0 point at infinity, we got kq over r for the electric point charge. For gravity, we would get negative gm over r. Okay, so the gravitational scalar potential, it's defined in a very similar way to how we define the electrostatic scalar potential. Next Monday, we're going to do a very important lecture where we're going to do a full comparison between electrostatics and Newtonian gravity and talk about why these things behave this way in general. Okay, so there's a very general way in which we can relate electrostatics and Newtonian gravity. There's a reason why we can do this. There's a reason why we can define these potentials, these scalar potentials, and these two things are so similar, so Monday is going to be a cool kind of summative lecture of these topics, all right? So on Friday, we're going to move on to gravitational energy. We'll see you then.
Just like in a circuit, we talk in terms of potential.
That's a very bad decision. That's like very bad.
I like the definition we had.